Hello. So we are on chapter 4 at 1.4 in the first chapter, and now we're going to look at negative and fractional indices. So we looked at general like whole number indices in the very first chapter with index laws. So say, for example, x to the a times x to the b. So if it's the same base with different powers or indices, we can add them. For example. So bear all that in mind, but what we can look more specifically now is more laws when we have negative or fractional indices. And so that if we have a fractional indice of, say, x to a half, that tells us we want the square root of x, okay? So anything fractional is to do with rooting. So x to the half is root x, but then say if we have x to a third, it wouldn't be root x specifically. It would then be the cube root of x, okay? So for example, obviously the cube root of 27 would be 3, because 3 times 3 is 9, times another 3 is 27, okay? And in general, x of 1 over n would be the nth root of x, okay? Okay, so that's fractional indices. Negative indices, so then if we then say x to the minus 1, uh, you just take the reciprocal, okay? So what the reciprocal means is you do 1 over the fraction, 1 over the number to get a fraction, right? So if say 1 over x, that gives us the reciprocal, okay? And in general, whenever you see a negative exponent, you want to just think about taking the reciprocal, so flipping it as a fraction, okay? And more generally, if you have a fraction already, say if you have 1 over a half, and you want to take the reciprocal of the whole thing, you take the reciprocal, so you flip it. Well, that would be 2 over 1. Okay, obviously then that could be 2, but that's the whole general premise of a negative indice. Okay, so those are the laws we're going to look at in this section. Okay, so let's have a look at some examples with this in action. So, okay. So the first question then, part A, we need to simplify x to the 3 over x to the minus 3. So again, this is going to combine the index laws we looked at earlier in the chapter with our new two indices. The two indices laws, we have fractional negative indices. Okay, well, we are again exact same. It's the index laws that we looked at last time. So if we're dividing the same number, which is x, the same base, again, as a reminder, a to the b, we call a the base, and the power it's raised by, well, the power or the exponent, okay? That's just a little reminder of the language you use. So that we have different powers. We have the same base, which is x, but all different powers. If we're dividing in this way, remember, we subtract the powers. So we're going to have x to the 3 minus, and then we have a minus 3, okay? But then if we have minus minus, that turns a positive. So that'd be x3 plus 3, which would be x to the 6. And that would be your simplified answer. Okay, let's have a look at part B. We have x to the half times by x to the 3 over 2. Okay, and again, exact same premise, even though we've got fractional indices, the exact same premise as with other indices. Because we're timesing with the different powers, we add the powers together. So we x of a half plus 3 over 2. Well, that's going to be x to the 4 over 2, because remember, same denominator. So we can just simply add the top number, just with regular fractions. And then that simplifies 4 over 2 is 2. So that'd be x2 or x squared. Okay. Cool. Let's have a look at part C. Then we have x cubed raised to the power of 2 over 3. And again, you should remember this index law, where we have, say, x to the a. So a whole expression raised to a power. You times the powers together, so a times b. Exact same premise here. We have x to the 3, but then it's all raised to the power 2 over 3. Again, we times them, no matter if it's a fraction or not, so we times the powers. So it'll be x got to 3 times 2 over 3. Well, 3 times 2 over 3 is going to be 6 over 3, which will simplify to x to the 2, which again will be x squared. Okay. Then part D, we have 2x to the 1.5. Remember, that's still a fraction, but it has a decimal form, divided by 4x to the minus 0.25. Okay, so I think the first step actually before we do anything is actually probably best to write it the fraction, right? Because this is division. So realise we can write this as a fraction of 2x to the 1.5 over 4x to the minus 0.25. That's just how we can flip from divisions to fractions. And it's best to do it here to really see what we can work with. And so then when we're in this situation, again, we've got numbers and x's, so let's separate them. So let's do the numbers first. So 2 over 4, firstly, the coefficient, if you will. 2 over 4 will go to 1 over 2, so half. Then we're going to have x to the 1.5 over x to the minus 0.25. So again, we're going to divide with just different powers, so we subtract the powers. So it's going to be x to the 1.5 minus of minus 0.25. And we can simplify that to a half of x. Well, minus 0.25 is adding it, isn't it? So 1.5 add 0.25 will be 1.75. And you'd be fine to leave it as that, but what you could say, you can write this as a fraction. Okay, so 1.75, well, that's going to be 7 over 4, right? And then part E, we have 2x squared minus x over x to the 5. Well, you could potentially factorize, potentially the top, because then we have an x on both sides. But actually, I think it's best to split the fraction up, okay, to do different fractions because we're subtracting. So firstly, this will be 2x squared over x to the 5. Um, minus x over x to the 5. So all it did is split. So now I can apply the index laws separately because now I have different powers, so I can subtract them in the usual way. But then with the first fraction, we have 2x squared over x to the 5. Well, I can just have 2, but then I subtract the powers. So 2 minus 5 will be x to the minus 3. And then for the second bit, minus x over x to the 5. Well, you could recognise we're just cancelling an x, but what actually is going on is actually, remember, the hidden power of 1 on the top. Okay, so it's on its own, just x, and there's a hidden power of 1. And that means we can do 1 subtract 5 to get x to the minus 4. And actually, the question would be fine if you leave it in that form. Okay, so we simplified it. Um, so there's no more like a big fraction going on. We simplified it. Okay, so those are what the indices. So hopefully you recognise it. What the whole idea is essentially it just works in the exact same way with index laws that we looked at earlier. It's just with fractions thrown in. It's the exact same sort of concept. Okay. Apologies. This is in editing. But I completely forgot to do part A. um. But let's have a look at it then. So again, the cube root of 125 to the x to the 6. Um, so again, everything is being cube rooted. So we can say the whole thing underneath the root, so 125x to the 6, is all raised to the power of a third, right? So the third power, that so everything's being cube rooted. And now what we can do here is actually again because we have a power outside the bracket, we can raise everything inside the bracket to a third. So it's kind of like the index law then, a to the n of no ab all raised to the power n. We split this up so that the power goes to each term separately. So then this will say 125 to a third, and then we're going to have x to the 6 Well, this would be times by x to the sixth of a third, okay? Um, well then, 125 of a third, again, that's the cube root of 125. And then x to the sixth of a third, again, we can times the powers because we have a bracket always by power, so we can times the powers together. So x to the sixth times a third. Well, okay then let's go back to this 125. The cube root, so it's saying what number times what's our 3 times gives us 125, and you should recognise that's a 5. 5 times 5 is 25 times by 5 again is 125. And then we have this times by x again, 6 times a third, so again we times the powers. Well, 6 times a third is 6 over 3, which is going to be 6 over 3 should be squared, right? It'd be 2, so it'd be squared. So that'd be your result for part A. So let's move on. Okay, so I want to explore this this is a very, very important idea, this is now. So then when we evaluate these its square roots, so for example, we have 4 to the half. Well, what this is saying is root 4. Okay, remember? What we discussed at the very start. We have x to the half is root x, or in general, x to the n, 1 over n is the nth root. Okay, remember that's what our fractional indices means. It's about rooting. So you can convert in this, but then you might say potentially, well, this is saying what number squared gives us 4. Well, you could say 2 or minus 2 because 2 squared equals 4 and minus 2 all squared equals 4 as well because of the idea that negative times negative is a positive. However, when we are just evaluating or simplifying an index in this way, you only want to take the positive, okay? That's how square roots work in this sort of sense. So we do not want minus 2, we just want 2 in this case, okay? Um, and the idea is when we just want a single answer, okay? We don't want multiple answers. When we evaluate something like this, I just want one single answer as an output, okay? Um, and this is how we take it. We take the positive, okay? Square root's positive. So yeah, so you just got one singular answer. The whole idea is we are not solving an equation, and we'll look at, and that's part A. Part B then says solve the equation, x squared is 4. So this is kind of saying the same thing, right? We want a number that is squared to give us 4. So it's the same sort of argument as part A. It's that same kind of scenario. Well, then you'd say x is plus or minus root 4, okay? So now we introduce a plus or minus, have the negative case as well. And hopefully you can see here, this is plus or minus. Well, what's root 4? Well, it's just 2. So that is why, that's a good idea to show why. We just take root 4 to just be explicitly one number, okay? Because we account for the plus or minus when solving here. But when we want root 4 directly on its own, we just want one singular answer, which is where we can just say root 4 goes to just 2, okay? But plus or minus is outside because the plus or minus arises from solving an equation. When we're solving, we want every possible case, every possible value of x that gives us the equation, right? That gives us x squared is 4. So you want to consider every case, okay? We want to solve to every single case that suits this equation. When we're just evaluating something, we just want one singular answer. Okay, we're not solving. We're not interested in every single case. We just want something. We just want one out. We just want one particular value. Okay. So then when you square a root like this, when you just have an actual number, we're not solving for anything. You just literally want to put square root something. You just do the positive, okay? But when you're solving equations instead, when you might need to square root, then you need to account for every possibility because you want every solution possible, right? So then you need to account for plus or minus. But hopefully you can see here the crucial difference is here. plus or minus comes from the value of x's that we want to find, right? But plus or minus is outside of root 4. So root 4 by itself just goes to 2. Root 4 is not plus or minus 2. Root 4 is just simply 2. And then we account for the plus or minus outside of the square root only because we're solving for x, because we're solving an equation. But root 4 by itself, hopefully you can see here, only goes to just 2. Because in this case, and by to reinforce what I'm saying, we are only evaluating, we're only just picking one singular value. We're not solving anything. And I guess this makes sense because a square root of anything, you're only going to get a positive answer. Okay, that makes sense. Square root should only output a positive. Okay, so that's the crucial difference of what I really hope you can get your head around that. Because when you look at other equations later on in the course or in the exam, you need to realise when it makes sense to take plus or minus, which should be coming from solving an equation, or when we just literally take the positive, or what just one particular value, which is when we want to evaluate something like this. Okay. Okay. And we'll look at more examples of this throughout the course. But this is the main fundamental idea. So I'm going over it now. So then you should have a rough idea of this as you look at other equations, other questions, other parts of the course, and so on. But that is the fundamental idea I want to explain. When you evaluate, when you're just evaluating, so just chucking a number, you want to root it, you should only get a single number, which should be positive. Okay, no plus or minus. Plus or minus will only come from solving an equation when you want all the multiple or all the sort of possibilities of the values of x. Okay. So yeah, I really want to drum that in. But with that in mind, then let's sort of look at these examples. Oh, and here we have numbers again, and it says evaluate 9. Now, you will have a calculator in all your exams, but I do still think it's a good idea to go over this question. First of all, because these are sort of the sort of indices that come up from time to time in exam. They come up fairly often. So it's a good idea to have back in the mind, well, 9 of a half equals so-and-so. 64 of a third equals so-and-so. So even though you would have calculator to do it for you, it's still good to understand why it is. And also it helps demonstrate what I've done up here. And so because we're just evaluating a number, we're evaluating, we're not solving anything, we're only going to get a positive answer. So there'll be no plus or minuses here. Okay, so part A, 9 of a half. So again, if we remember what a fractional index means, a half means we're just taking the square root, okay? And it'll be square root of 9. Well, root of 9 is just 3, and only positive 3, okay? Notice. We should only get positive out of a square root, okay? So we're not solving anything, we just evaluate, we just finding what particular value root 9 gives. And there we are, that's positive 3. Let's have a look at part B then. 64 of a third. Well, that's saying instead of the square root. So in this, a normal square root, by the way, you could write as 2. But it's kind of like a standard square root, the standard root. So root 2, we don't normally put the 2 in. It's kind of like exactly a bit like I said earlier when we have x. That is x to the 1. But we could just get rid of the 1 because it's kind of standard to know that x by itself or anything by itself just has a hidden power of 1. It's kind of like how technically a normal square root does have a 2 on there, but because it's a standard root, we don't tend to write it. But in this case, 1 over 3, we want the cube root, okay? So the cube root of 64. So that's saying what number times obviously times by itself 3 times gives us 64, and hopefully you realise that'll be 4, because then 4 times 4 is 16, and 16 times 4 is 64. Okay, part C, 49 to the 3 over 2. Well, okay, this one is a little bit of a step up, because it's not just 1 over something, we have 3 over 2, okay? But it's the exact same sort of concept. What this means is this is 49 of a half raised to the power of 3. Notice we can do it in this way because then we can use the index law AB to the n, where you times the powers together. So if you're raising a whole bracket by power, you times the powers together. And 3 times a half will be 3 over 2. And that is the whole idea of tackling fractional indices, where you got like both the top and the bottom number. Okay. So 3 over 2, we can split that up as firstly doing a half, and then timesing that result by 3, or cubing it. 49 over half, you should realise is 7, because root 49 is 7. So this would be 7 cubed, and then that's going to be 7 times 7 times 7. And you could just put that in the calculator, and that'd be 343. Okay. Yeah, so hopefully you realise what we've done there, and the fact that we can always split up an index like this by first doing the fractional part, so the rooting, and then the cubing. Okay, let's have a look at part D. We have now 25 to the minus 3 over 2. Okay, so when you got this, when you got something like this going on, we've got negative, we've got a fractional, and we've got like a cubing after. Well, firstly, the negative would mean we just simply take the reciprocal. So 25, the reciprocal should be 1 over 25, and then that'll be 3 over 2. And then we do the exact same concept. Well, then you're going to apply the square rooting, so it's going to be root 1 over 25 of to the power 3. Well, root 1 over 25, you should remember third law of Jesus. We will look at thirds actually next time. Uh, but for now, you should recognise we can split this up as root 1 over root 25. And so actually then we can individually square root the top and the bottom number. Well, root 1 is just 1, and root 25 is 5. And then that'd be all cubed. And so again, we cube in a fraction. You cube each number individually as well. So 1 cubed over 5 cubed, that's going to be 1. And then 5 cubed is 125. And that will be your answer. Okay, so part D is a really good answer, a really good sort of question that tests and brings everything together in one. And that's sort of the process you want to follow. Okay. Okay, example 11. So we are given y is 1 over 16 x squared. We need to express these two indices in the form of kx to the n. So k is a number and n is a number as well. Okay, so we need to resemble this sort of form in the question there. Okay, so firstly, y to a half. Well, I think probably the best way actually to write y is going to be uh, x squared over 16. So we literally explicitly make it clear x squared is the numerator and 16 is the denominator. And I think that might make things a little bit clearer when we take indices. So y to a half then, if we literally plug y in, that'd be saying x squared over 16 to a half. Okay. And so then we can apply the half separate of both top and bottom. So it'd be x squared to a half over 16 to a half. And obviously a half is saying the root square root, right? So root x squared over root 16. Well, root of a square is literally just itself. The square and the square root cancel. Okay. You can see that here. Because then we should be times in the powers because we have a bracket. So 2 times a half is just 1. Okay, so x to the 1 is just x. Or you could obviously recognize that squaring and square rooting are inverse, so they cancel each other out. So we have x, and then we have root 16. Well, root 16 is just 4. Okay, so we're left with x over 4. Okay, so to write it in this form clearly, well, it's already in this form, but you can make it very clear and say we can split this up as a fourth, because this is essentially a fourth times x, so it'd be fourth x to the power of 1 if you want, but clearly then k would be a fourth, a quarter, and n would be 1, okay? But you don't have to put the 1 there, but this answer should be perfectly fine, but yeah. Okay, let's have a look at part B. We have 4y to the minus 1. So again, I'm literally going to plug y in exactly where it is. So 4 and then a bracket for y, x squared over 16, and then done to the minus 1. Okay, well, before I times anything by 4, I'm still going to leave 4. But before I do anything with 4, I'm going to do it in the bracket, the actual index part first. So the x squared over 16 raised to the minus 1. So remember with minus 1, negative, we literally just flip it, we do the reciprocal. So the flipping x squared over 16 will be simply 16 over x squared. Okay, and now I times by 4. So again, 4 is kind of like 4 over 1. So it's kind of like times in fractions together. So that'd be 4 times 16 over x squared. Well, times 1, but that would just be x squared still. About 14 over 16 is 64 x squared. Okay, but it wants it in this form here. We have a fraction here, so that we still need to just get it as x without any fractions. But how are we going to do that? Well, you should recognise actually we can use inverse the negative reciprocal, the negative again, the negative power because x to the minus 2 uh, is simply 1 over x squared, right? So we just set reciprocal of x squared, okay? Um, and so we can simply say then this is 64x to the minus 2. Okay. And now I have it exactly in this form with no fractions or anything like that. Okay. So yeah, those are sort of the examples then. We can look at some more stuff now. For the exercise. So have a look then. Let me get rid of this to make room. Uh, so let's have a look at this question then. So I picked sort of questions from the exercise that are a bit different to what we've seen. Um, but you should be in a position now, if you understood this, to answer the exercise from the textbook or whatever from there. Okay. So part A, so it simply wants a value of 81 to a fourth. You could put that in the calculator, but what this is saying is the fourth root of 81. Okay. So that's saying what number times by itself 4 times gives us 81. And what you should realize if you play around with like 1, 2, 3, and 4, what they times to, you should spot this as 3 because 3 times 3 times 3 times 3 gives us 81. Well, that's 3 times 3 is 9, then times by another 3 is 27, then times 27 by 3 you get 81. Okay. Um, but yeah, that's simply that for 1 mark. And then part B, then a bit of a nastier question. Simplify x of 2x to the minus 1 over 3 to the 4. Okay, so simplify. So we need to kind of work with these sort of indices we've got here. Okay. Well, again, so we can say that's x. Then 2. Um, but then this is saying 2 times x to the minus 3 of 1 over 3. So that means x on its own, it has to take the reciprocal. So the reciprocal of x to the minus a third would be 2 times 1 over x to the third, okay? So it literally just took the negative out by doing the reciprocal, okay? And also the whole fraction itself isn't a negative because the negative indices only apply to the x. It's not applied to the 2 as well because 2x to the minus 1 is not the same as 2x to the minus 1. Okay, recognize that because the negative here is only, again, that's the index of x. It's not the index or the power of the whole bracket. The 4 is the power of the whole bracket. We will be applying the 4 to every number, the 2 and the x. But the minus a third, so the minus is only applying to the x. So we only take the reciprocal of the x part here. Hopefully you can realise that. Um, but yeah, so we got to this point, and that's all again raised to the 4. We can actually then bring the 2 in as into the fraction. So 2 is on the top and x to the third is on the bottom. Again, because we've kind of got a multiplying fractions, so we multiply the top, and then we can apply the power of 4. So then again, we'll deal with the x after at the end. So let's deal with the whole bracket part first. Kind of like bid maths, right? Bracket first, index second. So we deal with the brackets and the indices before we then deal with the x at the end. So we simplify the bracketing part. Okay, so then 2 over x to the third are the 4. So the fourth has been applied to everything inside the bracket, so the fraction inside. Well, again, we can spread the power of the 4 to the top and the bottom separately. So 2 raised to the power 4 and x to a third, all raised to the power 4. Well, then we can evaluate this, can't we? Because then x of 2 to the 4 is going to be 2 times 2 times 2 times 2. Well, that's going to be 16. Okay. And then x to a third of a 4. Well, that's going to be times in the powers, right? Because then we're going to have a third times 4. That's going to be x of 4 over 3. Okay. Because a third times 4 is 4 over 3. Okay, well now we can kind of bring the x in and see what we can do from there. So then if I simplify it again over here, well then we're kind of saying x times 16 over x to the 4 over 3, right? Because x is outside, x is times in everything inside the bracket. Well again, that's just going to be 16x over 4 over 3. But how can we simplify this? Well again, now because we're divided by the same number x, we can subtract the powers. And notice, again, this is going to be a power of 1 because it's just x. You can subtract 1 by 4 over 3. So that'll be 16 x to the 1 minus 4 over 3. Well, that's going to be 16 x to the minus the third, okay? That's just subtracting fractions, okay? So 1 is the same as 3 over 3. 3 over 3 take away 4 over 3 is minus 1 over 3. And we could leave that there, actually, because it's kind of simplified. Generally, when we want to say simplify, we want it to look as kind of nice as possible, so without any fractions, and there's only like a single value of x. Whereas here, obviously, we've got two parts of x, two x's here, so it's a lot more complicated than the form we got at the end. Okay, and it's kind of simplified, could look quite presentable. But yeah, but alternatively, I guess you could evaluate the power if you wanted to. So that's 16 over x to a third, and then that's 16 of cube root of x. That is up to you. But generally, if it's written in this sort of form where it's just a single x, no fractions or anything like that, that's kind of good enough for us. Okay. But also, you could be expected to again evaluate a more complicated one again with fractions, kind of like what we did before. But this I think is a bit more involved. But again, exact same principle. So part A, we have 8 over 27. So now we deal with fractions, all raised to a power of 2/3. So again, we're going to apply. Again, it's kind of saying 8 over 27 to the power of a third, so do the fractional bit, and then it's all squared. Because then a third times 2, remember the times the powers, it still remains 2 over 3. So let's deal with the denominator, the fractional part first, the third. Well, what's the third mean? Well, it's cube rooting, and we can cube root both the top and the bottom. Again, then that's going to be all squared, because then we've got the 2 at the outside. So again, cube rooted it first, and we're going to square it. But we can evaluate this, right? So what's the cube root of 8? That's going to be 2. Remember, looking for a number that times by itself 3 times to give us that number. So 2 times 2 times 2 is 8. And the cube root of 27 is 3, because 3 times 2 times 3 is 27. Okay, and then we're going to square it. And then that's just simply saying 2 squared over 3 squared. Uh, and that would be 4 over 9. Okay. And remember, that is the case as well, because 2 over 3 squared or of any power at all, I guess. That's a whole number. It's kind of like repeating itself. So 2 over 3 times by 2 over 3. That's what a square means. You times it by itself 2 times. If it was to the power of 3, you times it by itself 3 times, and so on. But then obviously, if you times in like this, multiplying fractions, you just times the top and the bottom number by itself in this way. Well, that's just going to be 2 squared over 3 squared. So it will. So you can just jump right to the chase and say, well, 2 over 3 squared. You can just split the square up to the top and the bottom separately. Okay. And that's our result. Okay. For part A. Then part B, we have 9 over 16 to the minus 3 over 2. So now we have a minus. So again, the best thing first is to account for that by taking the negative and taking the reciprocal, sorry. So we flip the fraction to 16 over 9. And now we just left with 3 over 2, so that gets rid of the negative. And now it's exact same process as part A. So again, I'm going to account for the fractional part. So the half bit first. So a half is the roots, just square rooting. So root 16 over root 9. And then that's going to be raised to the power of 3, okay? Because the top number is 3, and then it's 3 over 2. Because remember this one, this is saying 3 over 2 is the same as 3 times a half, okay? So a half is the fractional part, and 3 is obviously the power that we're cubing, right? So we can do the fractional part for a half, which is why we're rooting here, the top and the bottom, and then we can cube it after to get 3 over 2. Okay, well, again, we can value what's in the bracket. So root 16 is going to be 4, and root 9 is 3. And then we're going to be cubing. And again, that's going to be 4 cubed then, over 3 cubed. Well, then that we can just simply evaluate. What 4 times 4 times 4 is going to be 64. And 3 times 3 times 3 is 27. And that is the fully evaluated version, okay? Um, And there we are. And again, to reiterate what I said earlier about only doing the pluses, by only taking the positive case when we're square rooting or whatever, when you're evaluating, not solving. Again, notice here when we square rooted, we're not taking plus or minus, we're just simply taking the positive. Okay, and then we only get one answer at the end of it, which is what we want. Okay. So that's on the question. The questions from the textbook, or the questions that really demonstrate your knowledge and make you learn and understand the content. But now let's actually apply it to an exam situation, right? And this was an exam question using our index laws that we just learned. And it says, given 2 to the x times 4 to the y is 1 over 2 root 2, express y as a function of x. So that just means express y in terms of x, right? But what you kind of notice here, we've got all these indices, 2 to the x times 4 to the y, 1 over 2 root 2. And what you should notice actually is that everything can be written in terms of 2, because I know 4 is 2 squared, but also know that 2, root 2, sorry, is 2 to the half, right? Remember, the fractional of a half means you're square rooting. So I can kind of rewrite everything in terms of 2 with different powers. Okay, that's really the only thing I can do at the moment, this sort of question. So let's do that then. So if we start from here, 2 to the x times 4 to the y is 1 over 2 root 2. Well, that 2 to the x, okay. But then 4, as we saw here, is 2 squared. So I can literally substitute that in to say, well, 4 is 2 squared. And then that's all raised to the power of y, okay. And then 1 over 2 root 2. Well, 1 over 2, okay, that's 2 to the 1. But then root 2 uh, is going to be 2 to the half, right? And we can kind of substitute that in as well, that result. Um, and then I can simplify from there. So notice I've got everything in terms of 2 now, but I just need to work a bit more to kind of simplify this whole expression. So then 2 to the x and then 2. Again, this is going to be the index law then. 2 squared all raised to the power y. I have a bracket all raised to a power, so we times the powers together. Okay. So that's one of the index laws, if you remember. So that's going to be 2 times y, but I can say that is just simply 2y. Okay, remember algebra. And then that's going to equal 1 over 2. Well, this is 2 times 2 over half. We're not raising by a power here, we're just simply timesing one number with another. Even though there's a bracket, remember it's just simply 2 times 2 to the half. Okay, that's what that's saying. Well, if we're timesing with different powers, we just add them. And remember, 2 is simply 2 to the 1. So 2 to the 1 plus a half is 2 to the 1 add a half. Well, that's going to be 2 to the 3 over 2, okay? 1, remember, is 2 over 2. We can write as a fraction, which is then 2 over 1 over 2, which is 3 over 2, okay? So that'd be 2, 3 over 2. Okay. I'm getting a bit closer now. It's more simplified. Okay, well, now I noticed that actually I have 2 is the same base, right? We have 2, which is same, being multiplied by different powers. Although there's x's and y's, the whole concept is we still times them by different powers, but 2 is the same. So again, that's going to be the index law of a to the n times a to the m is going to be adding. So a to the m add n. So we can add the powers to then say we have 2 of x add 2y. Then equals, well, actually, again, we have a fraction here, and it's 1 over 2 to the 3 over 2. That is exactly the reciprocal, isn't it? So, I can say this for 2 to the minus 3 over 2. If I want to express this as a reciprocal of 2 to the 3 over 2, I could just whack a minus on, okay? And to recall that is because 2 to the minus 1 is a half. And so then if I have 2 to the minus 3 over 2, that's going to be 1 over 2 to the 3 over 2. Okay, just to reiterate. Okay. Well now, well, we're in a really good position now because I have the same base 2, and that they're equal to each other. Well, if they're equal to each other and the 2 is the same, the base, that means the exponents have to be equal to each other, so the powers. That means simply then x plus 2y has to equal minus 3 over 2. But now we're in we've pretty much done it now, right? Because it said express y in terms of x, right? Um, but that's what we're going to do then. So we just need to get to y on its own. Well, then how are we going to do that? Well, let's first take away x to both sides. But then we're going to be left with 2y is simply minus x minus 3 over 2. And then, well, that's 2y, but we want y. So then simply we're just going to divide by 2. So it's going to be a half then. Or you could say, I guess, minus x minus 3 over 2 over 2. And then we can split this kind of fraction up into 2 parts. So again, the minus x first, so it's going to be minus x over 2. Or that's just simply a half x, okay? And then we're going to have minus 3 over 2 over 2. Okay, well, actually, this might look a bit complicated because we've got a fraction in a fraction, but obviously you can put this all in the calculator. But to see how that works, I realise we can kind of express this again as division. So this is saying 3 over 2 divided by 2 in this way. And I put that as a bracket there. I'm going to do that over here actually. 3 over 2 divided by 2. Well, then if you remember KFC, that's keep the first fraction, change the sign, and flip the second fraction. So flip 2, take the reciprocal to 1 over 2. Okay, but then if times across, then you get 3 over 4. Okay, so that's how you can convert like a nasty fraction of, say, like we had there, 3 over 2, by just literally converting it as an actual division like this to help you realise fully what's going on there. Well, as we saw, that just goes to 3 over 4, so it'd be minus 3 over 4. And there we are. That is our answer. That is y in terms of x. Okay. It says specifically as a function, but don't get bogged down by that. Because that all that's saying in the function is if I plug a value of x in, what's the value of y? Well, that's just asking for the equation, right, for y in terms of x. Okay, so that's the exam question applying it. Maybe a bit tricky. It pulls a lot of effort together. When you, it might be a bit of step, obviously at first, when you start the course, obviously at the start of the course. But when you get used to it and you get used to the course, you get used to the questions, the harder topics. Um, you get used to this sort of algebra. So don't be too put off by it at the moment. If this was a bit of a bothersome, tricky question, um, but yeah, that's just the sort of like level of index laws you'd be expected to use and the level of algebra you'd need for the exam. And it's a good question to actually put into practice the topic we've learned. And it's really good in my opinion anyway to really test getting an actual exam question to make sure you actually are exam ready and you really know the topic in sufficient enough detail. And yeah, that's hopefully this has helped. But I am going to leave that there.